All right, let's go ahead and solve the first one. Separation of variables literally is separating the variables and grouping, regrouping I call it. So I'm going to do a very simple algebra step first. Cross multiply. Group the y's with the dy's, and I'll rearrange when I need to, group the x's with the dx's. So I'm going to make this look a little nicer. Y dy equals negative x times dx. Integrate both sides. They are simple antiderivative problems to find. So what I mean by that, everyone, is they are basic either memorization facts or add 1 to the power, divide by the power rule. That's it. We'll do that here. On these two, it's just going to be an add 1 to the power, divide by the power. Add 1 to the power, divide by the power. Because we have no definite little limits, and we're not doing area, we're just finding a generic formula for the function, we're going to put the plus c on the right side of the equation. If you do these the same every single time, when you get to your practice free response questions, you can go through those pretty quickly. It's the same process. It's a procedural process on these problems. It's the same thing every time. I need to find C. Here's how we're going to get C in this problem. We're going to use what they call the initial condition. The initial condition is written typically one of two ways. It's either written as, like I have up here, y equals 3 when x equals 4, or it's written like this, f of 4 equals 3. So this and this are the same thing in notation on a calculus question. We plug in 3 for y and 4 for x and solve for c. 3 squared over 2 equals negative 4 squared over 2 plus c. Nine over 2 equals negative 16 over 2 plus c. I'm going to leave it as a fraction on the right side on purpose so I can just add it to the other side, keep the common denominator the same, and I'm done with finding c. I'll add 16 over 2 then to the left to solve for c. C equals how much? Yeah, 25 over 2. I'm just going to leave it like that. I don't need to worry about simplifying it. I don't need to worry about decimals. I'm just going to leave it like a fraction like it is. I'm going to go back up here, plug in C, and solve for y like an algebra equation. The calculus part of the problem is finished. After you've done the second step of find the antiderivative, the rest of it is going to be some algebra and substitution problem of solving for C. The last step is our algebra step. So I think I'm going to first multiply everything by 2 to get rid of the 2 over here in the denominator. We like that because that's kind of nice, right? That gets rid of all the 2's there. And then to get y by itself, square root both sides. we have one solution we need to look at. Where are we looking at? The point we're looking at is 3, 4. And so what quadrant is 3, 4 in on a graph? First quadrant. So we want to be in the first quadrant for our solution. So I'm going to choose the positive one or the negative one? Positive. Good. So this is our function, everyone, that we have for that differential or derivative. That one's done. Now, the cool thing I like about these problems, honestly, is that when you are looking at solving the problems, again, they're very procedural. In other words, you follow this step, this one, and you can get through the problems as long as you know your basic antiderivatives in solving them. And then we can solve pretty much any kind. This is what I call the first style of question. Next, we'll look at what I call the second style of question. Any questions on this one, first of all, that you have for me? Okay. So let's do this one. This is a 2x times y. So this is a direct one. Slope field graph. We just looked at the graphs of these. We did an x over y or negative x over y. We looked at x times y, slope field graphs. Now we're going to solve this one. It looks a little different, but I'm going to start the same way I did before. I'm going to put it over 1, so it looks like the exact same thing we started with on the last problem. Cross multiply and regroup. I want my x's with the dx's and my y's with the dy's. So let's see what we get when we initially cross multiply. 1 dy or dy equals 2xy dx. Now I still have this y here, so I'm going to divide it out. So it's with the dy over here. My initial problem is dy over y equals 2x dx. Integrate. In my opinion, I think it's easier if we keep the y's on the left always and the x's on the right. If the problem you encounter is a context problem where they don't use x and y, figure out which is the first variable and which is the second, which is the dependent and which is the independent variable, and then just rename them to make it look just like these. That's the simplest way to do these. Now this part here might be a little bit tricky, so we have to think about what that is. dy over y is the same as saying dx over x. It doesn't matter the variable when we find antiderivatives. But this is the same as saying 1 over x dx, just like this is the same as saying 1 over y dy. Now we know there's something that has this as a derivative. What's the something that has that as a derivative? Natural log of x. Very good. So instead of natural log of x, I'm going to call it natural log of y. On the other side, it's just a very basic add 1 to the power, divide by the power. We leave the constant, remember. So when I do that, notice that the 2's over here will cancel out. Put the plus c on this side of the equation again with the x. Here's the big question in this problem. How do you get rid of natural log? What's its partner or its inverse operation in order to get rid of natural log? E. Very good. So let's use that to our advantage. E and natural log are inverse functions and cancel each other out. So let's do e to the ln of y over here, because I have to get it just in terms of y equals, remember, to get a function equation. Or a solution curve is what they typically call it in the AP world. I'm going to take e to both sides here as well. Now the left side becomes very basic. E and natural log, like I just said, cancel each other out. So e to the ln of y just becomes y. On the right side, I still need to figure out yet, and I haven't found what C is. So we're going to do what I call in calculus the magic step. We're going to rearrange this piece right here, just that part of it, and write it as two separate things. So I'm going to call it E. So this is a like a pre-algebra algebra idea that when you look at your exponents, when I multiply the exponents separately, we add them together. So here's how this would look. So this is what the same thing, all I've done is rewritten it. I haven't solved anything, I've just rewritten. E to the x squared plus c is the same as e to the x squared times e to the c, because we learned that we add exponents. So just going backwards from that pre-algebra exponent rule. Now, that's not the magic step yet. The magic step is that in calculus they say that c is what they call, as we mentioned earlier, an arbitrary constant. And so we're going to rename an arbitrary constant is just a constant. So we're going to, here's the magic step, we're going to call, and you can even write this down and call it the magic step, we're going to rename e to the c as simply an arbitrary constant c. I'm going to go back up to the original problem and look at what my initial condition was to find c. And at that point, once we get c, we're pretty much done. Y equals 3 when x equals 0. Plug in 3. Oh, not 3 here. Plug in 0. Zero squared is 0. What's e to the 0? 1. Anything to the 0 power is 1. So what does c equal? 3. When I write my answer, I'm going to go back to the magic step right here. And I'm going to write my final answer using, or plugging in, the c value. So y equals 3e to the x squared, or e to the x squared times 3 is the solution curve, or the function that fits that differential or derivative dy dx 2xy that we started with. On this one, we don't have to worry about plus or minus like the other one because it's a different kind of curve. It's an E curve. Oh, the other thing I'll mention, because this is something important, sometimes when we're working with E, and I'm going to mention this here, and I'm going to just add it to this just for a moment, everyone, so you can see this. Technically, when we solve it, remember that we can't have, in logarithm language, we can't have a negative base, right? There is no such thing in logs as a negative base. And so one of the ways they get around that in calculus is to use absolute value. When you do e to the ln of y step, a lot of times they use the absolute value on there. I guess if it were me and I were writing down a solution on a piece of paper to an AP question, I would probably do the absolute value piece, but the reason that we don't need it at the end is because look at where we are. Okay? Look where we are. We're in the positive, again, quadrant 1. So it's okay on this one to drop the absolute value because we're positive. Now, if we were somewhere like in a quadrant 3, for example, where they're both negative, then we may have to revisit that idea and just think about, okay, if I'd have to probably use the negative of it if I'm in a different quadrant. A lot of times you're not. You're going to be up in the nice little quadrant 1 up there. Okay, that's what I call the second style of question. The first style is just a basic style question, solve for c, plug it in, antiderivatives. The second style question uses the natural log and the e function, where we have to use the magic step. Last one. dy dx equals cosine squared of y, and y equals 0 when x equals 0. So this is our initial condition. We'll use that to find c. We'll start by simply separating. Before I do that, I'm going to rewrite this. All right, let's separate. Cross multiply. 1 times dy is dy. Cosine of y squared, or cosine squared y. It doesn't matter which way we actually write it, to be honest, at this point, times dx. We have to group the y's with the dy's and the x's with the dx's. I need to bring this over to the other side. Here's what I have so far. dy over cosine squared, or cosine y quantity squared, doesn't matter again which way you write it, equals, I'm just going to call it dx, or 1 dx. If it bothers you to just have a dx, put a 1 there for the antiderivative purpose of it. Now, it looks a little scary because we don't know how to deal with cosine squared, but we do know how to deal with 1 over cosine squared, because what is 1 over cosine's partner? What's his partner? Secant. Remember, c goes with s. So secant squared we are familiar with. So I'm going to rewrite it. So what is the antiderivative of secant squared? What is it the derivative of? Tangent. Good. On the other side, it's just x. Antiderivative of 1 is just x, because derivative of x is 1, plus c. Once again, we need to find c, and then we need to finish and solve, and I'll show you how to write the answer when we're done. So let's go ahead and plug in 0, 0. We need the tangent of 0. Zero. Oh, that's a simple one, right? 0. Okay. So we have tangent of y equals x plus 0, or x. I'm just going to write it, tangent of y equals x. To get y by itself, we do the inverse operation. So y would equal inverse tangent of x, and that's it. That's our antiderivative. Or, sorry, that is our solution curve for the derivative using antiderivatives. Any questions on this one? This one's more like the first one. It's just a different type of function to work with, but it's more like the first problem where you're just taking antiderivatives of both sides. The other thing to remember, what people sometimes get a little bit stuck on is on these problems where you have the ln problem and you have to use the e. Wait until, this is always the question, is when do I plug in the numbers? Wait until you get to the magic step and then plug in to find c, and then go back and use that step to rewrite your equation. Okay? Otherwise, you're going to end up with a just a struggle in the problem, and it doesn't need to be a struggle on it. Anything you want to ask me about from the separation of variable problems?